Good day, everyone. This is the laboratory report presented by Group 1 of CPE 2201 for the Laboratory Experiment 2 as part of the course requirements. Next slide. This is the transistor small signal amplifiers and frequency response. Next slide. For the experiment 2, first is the transistor small signal amplifiers. For the introduction, in electronics, signals often come in very small forms that are too weak to be directly useful on their own. This is where transistor small signal amplifiers play a crucial role. They are designed to take these tiny input signals and increase their strength without significantly distorting their original shape. By using transistors operating in their linear region, these amplifiers make it possible for devices such as radios, communication systems, and audio equipment to function effectively. For the objectives of this laboratory report, number one is to measure and differentiate the no-load and loaded gain of a transistor circuit. Number two, to measure the value of the input and output impedance of a transistor amplifier. And lastly, to interpret the effects of source and load resistances. For the materials and equipments that is used in this laboratory experiment, the first one is the adjustable DC power supply, the function generator, resistors, transistor, breadboard, connecting wires in the size number 22, the ground, next slide, the multimeter, a dual channel oscilloscope, and the simulation software which is the multisim. Now for the voltage gain. The figure 1.3 shows the BJT fixed bias circuit with the oscilloscope. Next slide. And for the figure 1.6, which is the voltage divider bias circuit with oscilloscope, so the figure above shows a voltage divider bias circuit connected to a dual channel oscilloscope, and the oscilloscope is used to compare the input signal from the function generator with the resulting output waveform from the collector of the NPN transistor. Now for the figure 9, which is the 1.9, which is the JFET emitter bias circuit with oscilloscope. Next slide. And now, this is the formula used to compute the voltage gain. For the manual computation of the voltage gain of the BJT fixed bias circuit, we can see that the value in the input voltage of the BJT fixed bias circuit is 9.985 millivolts, and for the output voltage is 1.719 volts. So finding the voltage gain, we use the formula AV is equals to output voltage over input voltage. We substitute the given, which is 1719 millivolts over 9.985 millivolts, which results to 172.15 voltage gain. And now for the voltage gain of the voltage divider fixed bias circuit, the input voltage is 9.984 millivolts and the output voltage is 588.909 millivolts. Finding the voltage gain, we use the formula AV is equals to V out over V in, and substituting those given, we have 588.909 millivolts over 9.984 millivolts, which results to 59 voltage gain. And now for the voltage gain of JFET emitter bias circuit, the given is for the V in is 19.907 millivolts, and for the V out or the output voltage is equal to 19.664 millivolts. Finding the voltage gain, we use the formula AV is equals to V out over V in, wherein we substitute the given, which is 19.664 millivolts over 19.907 millivolts, which results to 0.98 or 1 voltage gain. And now for the table 2, which is the data comparison of the manual computation of the voltage gain of BJT fixed bias circuit, voltage divider fixed bias circuit, and JFET emitter bias circuit. As we can see in the table, the BJT fixed bias circuit delivers the highest performance in terms of raw amplification and achieving a voltage gain of 172.15. So the voltage divider bias configuration demonstrates a deliberate trade-off, reducing the voltage gain to 59 in exchange for significantly improved circuit reliability. And for the JFET emitter bias or the source follower, it functions as a unity gain buffer. So as evidenced by its near identical input and output values, which results in a gain of approximately 0.98 or 1, its primary advantage is it is extremely high input impedance.
So for figure 2.1, next slide please, which is the BJT fixed bias circuits. For the circuit configuration, NPN transistor denoted by Q1 is a fixed bias setup, biasing a single large 330 kilo ohms base resistor R2 connected to to an 8-volt supply. The oscilloscope shows a noticeable difference between the input and the base signals, indicating a measurable current flow into the base. And for the figure 2.2, VGT voltage divider bias circuit. For the circuit configuration, it is a biasing which is uses a voltage divider for establishing a stable DC operating point. Next slide, please. And for the figure 2.3, which is the JFET emitter bias circuits, for circuit configuration, the transistor JFET Q1 is utilizing a 1 million ohms gate resistor 4. Biasing mechanism of it is with a 510 ohm source resistor R2 creates the self-bias voltage, but it is bypassed by an AC analysis by C3. And for its data analysis and relationship, the JFET stage provides the highest input impedance, nearly matching the 1 million ohm value of R4. This occurs because the internal gate impedance of the JFET is exceptionally high, often in the giga-ohm range. Next slide, please. Now, to compare the circuits fairly, each simulation uses a 100 ohm sense resistor to measure the input current, and the relationship used for all manual computation is with the displaying formula shows in this table. Now for this figure, we see a bipolar junction transistor and fixed bias configuration. This setup is using a 33K, and the result is an input current of 0.39 microamperes. The comparison, next slide, is and then and then for the comparison, with here, even though the bias resistor is huge, the input impedance is only 11.77 kilo ohms. This is because the total impedance is dominated by transistor's internal base resistance, which is much lower than the 330 kilo ohms resistor in parallel with it. Now, in the previous slide, please. In the voltage divider bias analysis, introduce more complex voltage network, which is the setup is critically the emitter resistor with R5 is completely bypassed by the capacitor. Now, for the data, we see a large voltage drop from 4.9895 millivolts down to 4.801 millivolts, which the result which would be resulting a produce a highest input current for the tree, which is 1.885 milliamperes. The comparison, next slide, please. The comparison consequently in this circuit has the lowest input impedance at 2.55 kilo ohms because the emitter is bypassed and there is no swapping effect in the increase of the base resistance, and the parallel combination of the bias resistor further pulls the total impedance down. For the JFET emitter bias analysis, which is in figure 2.3, which is the junction field effect transistor million, I mean 1 million 1 million ohms. The data voltage drop is almost non-existent, moving from 9.9925 millivolts to 9.992 millivolts. The result is the input current is negligible into 0.005 milliamperes. Then next slide, please. And the comparison between those yields a massive input impedance, a 998.4 kilo ohms, because the JFET's gate is reverse bias and it draws almost zero DC current, making it the 1 million ohms resistor the only significant factor for this staged AC impedance.
Now let's look at the output impedance. The output impedance shows how well a circuit can drive a load lower values, mean better performance. In this experiment, it is determined by measuring the voltage drop across a 100 ohm sense resistor. Next slide, please. Let's begin with figure 3.1. This shows the output impedance of a BJT fixed bias circuit. A small AC signal is applied to the base and travels through the collector and the 100 ohm sense resistor. And now if we look at the oscilloscope, we can see that the output signal is slightly lower than the source signal. This small difference indicates a minimal voltage drop across the resistor, and as a result, we can conclude that the circuit produces a relatively low output current. Next slide, please. And moving on to figure 3.2, this circuit uses a voltage divider bias configuration, which improves stability. Here, the oscilloscope shows a much larger gap between the source and output signals. This is important A large voltage drop across the sensor resistor means that more current is flowing. So compared to the fixed bias circuit, this configuration clearly delivers higher output current. Next slide, please. In figure 3.3, we have the JFET emitter bias circuit. The AC signal is applied to the gate and flows through the drain and sensor resistor. Observing the oscilloscope, the difference between the input and output signals is again very small, and in this table is the manual computation of the output current of BJT fixed bias circuit, voltage divider fixed bias circuit, and JFET emitter bias circuit. And the formula we use to calculate this is that is that the output current is equals to V source minus the output voltage over R sense. Next slide, please. And for table 8 is the comparison. This compares the output current of all three circuits. First, take note that the input voltage is constant at 4.99 millivolts. This ensures a fair comparison. The BJT fixed bias and JFET circuits both produce a 1.80 microamperes. However, the voltage divider circuit stands out, delivering the highest output current at 2.2 microamperes. This clearly shows that the voltage divider bias allows more current to flow due to its stronger and more stable biasing. Next slide, please. Next slide. In this table, the manual computation of the output impedance of BJT fixed bias circuit, voltage divider bias circuit, and the JFET emitter bias circuit. The formula we use is the output impedance is equals to VO over the IO. And next slide, please. Finally, in table 10 presents the output impedance of each circuit. Here, the voltage divider circuit again stands out, having the lowest output impedance as approximately 2.17 kilo ohms. This means it can drive loads more effectively. In contrast, both the BJT fixed bias and JFET circuits have higher output impedance at around 2.67 kilo ohms. Overall, this confirms that the voltage divider bias circuit offers a better current delivery and improved performance when driving a load. Next slide, please. And now let's talk about the effect of load resistance on voltage gain. Next slide, please. In figure 4.1.1, 1 kilo ohm load resistor. The oscilloscope shows an input voltage of approximately 4.96 millivolts and an output voltage of approximately 347.23 millivolts. To find the voltage gain, we divide the output by the input. 347.23 millivolts divided by 4.94 millivolts gives the voltage gain of 70.29. In figure 4.1.2, a 2.2 kilo ohm load resistor is used. The input voltage is approximately 4.97 millivolts, while the output reaches about 1.08 volts. For the hand-solved calculation recorded in table 11, using an input of 4.98 millivolts and an output of 556.36 millivolts, we divide 556.36 millivolts divided by 4.98 millivolts gives a voltage gain of 111.72. The higher load resistance reduces the loading effect, allowing a greater portion of the amplified signal to appear across the output, producing a substantially larger amplitude. Next slide, please. And now in figure 4.1.3, a 3.3 kilo ohm load resistor is used. The input is approximately 4.98 millivolts, and the output rises to about 1.52 volts on the oscilloscope, giving a gain of around 305. Next slide, please. And for figure 4.1.4, a 5 kilo ohm load resistor is used. The input is approximately 4.98 millivolts, and the output reaches about 1.82 volts on the oscilloscope, and for a gain of roughly 365. For the hand-solved value in table 12, using an input of 4.97 millivolts and an output of 768.83 millivolts, we compute 768.83 millivolts divided by 4.97 millivolts equals a voltage gain of 154.69. With a 5 kilo ohm load, the circuit experiences minimal loading effect, and the amplified signal is largely preserved at the output. This represents the highest gain among the 5 configurations tested. Next slide, please. For figure 4.1.5, a 4.7 kilo ohm load resistor is used. The input is approximately 4.97 millivolts, and the output reaches about 1.74 volts, giving a gain of around 350 from the oscilloscope. And these are the solutions of what I said in the figures. Next slide, please. This is for the 5 kilo ohm load resistor and for the 4.7 ohm load resistor. Next slide, please. And in summary, Table 13 consolidates all results, and the voltage gains are 70.29 at 1 kilo ohm, 111.72 at 2.2 kilo ohms, 137.39 at 3.3 kilo ohms, 153.89 at 4.7 kilo ohms, and 154.57 at 5 kilo ohms. And the trend is clear and consistent. As load resistance increases, voltage gain also increases. A larger load resistor allows a greater voltage swing at the output for a given transistor current, resulting in higher gain. And the gain of the amplifier is directly and positively influenced by the value of the collector load resistor. Next slide, please. And now let's talk about the input and output voltage in a BJT fixed bias with a sense resistor.
For the part 2 effect of source resistance on a voltage gain. For next slide. For the figure 4.21.1, 100 ohm sense resistor, the oscilloscope reads an input voltage of about 4.99 millivolts and an output approximately 1 volt. For figure 4.2.2, 220 ohms sense resistors, the input remains about 4.99 while the output drops to 922.91 millivolts. Dividing the two, we get 184.95 with and the output amplitude decreases compared to the 100 ohm case, and the waveform shows increased distortion at the peaks as the larger sense resistors merge strongly impacts the circuit's biasing and further limits the transistor linear operation. Next slide. For the figure 4.2.3, 330 ohm sense resistors, the input still remains 4.99, where the output was 860.21 millivolts. Dividing both, we get 172.39 with respect to the input voltage. And the output waveform shows more noticeable flattening and irregularities indicating the transistor is no longer operating in its linear region. Current load is being restricted, compressing the output signal and greatly reducing application effectiveness. Next slide. For the 4.2.4, 470 ohms resistor, the output drops to approximately 791.35 millivolts from the same 499 millivolts input. Dividing both, we get 158.59 with respect to input voltage. And the waveform shows significantly flattening and uneven peaks, indicating the transistor can barely amplify at its operating point. The signal is heavily compressed and overall amplifier performance is significantly reduced. Next slide. For the table 14, next slide. And 15 record the voltage gains with respect to the input voltage for 0.44 at 100 ohms decreases to 184.95 at 220 ohms, drops further to 172.39 at 330 ohms, and reaches its lowest value of 158.59 at 470 ohms. Next slide. The table 16, next slide. Table 17 present the same data recalculated with respect to the source voltage using 5 millivolts as the reference input yielding gains and 184.58, 172.04, and 158.27 respectively. Both sets of data confirm the same inverse relationship. As sense resistance increases, voltage gets consistently decreases. This is attributed to the voltage dividing effect of the resistance resistors. As its resistance grows, a greater portion of the source voltage drop across it, reducing the effective input seen in a transistor-based terminal, while the output voltage remains comparatively less effective. Next slide. For the part 3, combined effect of proportional sense and load resistance. Next slide. For figure 4.3.1, 100 cents and 1,000 kilo ohms load, the oscilloscope reads about an input of the same 4.99 millivolts and approximately output of 270.69 millivolts. Dividing both, we get 54.25. And against for the 5 millivolt source reference, 270.69 millivolts, dividing it by 5 millivolts gives 54.42. For the figure 4.3.2, doing the same steps in the 4.3.1, dividing it both, This is notably jump from the first configuration, the larger load resistance enhances the output voltage swings to a degree that outweighs the attenuation it reduced by a increased test resistance, resulting in a net improvement in gain. Next, for the 4.3.3, we use 330 ohms for sense resistor and 3.3 kilo ohms for load resistor. With the same process for the previous figures, we divided it and gain continues to rise as the 3.3 kilo ohms load still dominates by pushing the output voltage higher despite the growing sense resistance. Next slide. For the figure 4.3.4, the 470 ohms resistor and 4.70 kilo ohms load resistors, and by doing the same step in the previous, we get the rate of the gain improvement has clearly slowed compared to the earlier steps, suggesting that the increased sense resistance is beginning to offset the benefits of the larger load. Next slide. And this is the data computation of each figure. Next slide. Table 18 and 19 summarize the voltage gain with respect to input voltage for the combination configuration 54.25 at the first pair, 83.03 at the second, 94.79 at the third, and 100.71 at the fourth. Next slide. For the table 20, next slide. And 21, repeat this analysis with respect to the source voltage using 5 millivolts as the reference yielding this 94.14, 83.36, 94.60, and 100.51 respectively, probably when measured against the source voltage. Next slide.
So for the laboratory experiment 3, next slide please, we will discuss about the frequency response. So next slide please. So for the introduction, a transistor are 3D has a terminal devices which use for amplification and switching by controlling current or voltage. So just like in BJTs, a small input current controls a larger output current, enabling signal amplification. So in this experiment, a transistor amplifier is analyzed and observe how gain changes with frequency and to determine the cutoff frequency and bandwidth. Gain is not a constant as low as frequencies are affected by the capacitor and high frequencies by internal resistors effect. So for the objectives, we are going to distinguish the effect of frequency to the gain of a transistor circuit. The second is to determine the high, low and high cutoff frequencies and bandwidths of a transistor amplifiers. And the third one is to draw the bold plot of the amplifier circuit. Next slide, please. So just like in the experiment 2, our materials and equipment is just the same as the previous experiment. Next slide, please. All right, next slide, please. So for the procedure part,
So for the procedure, first, we reconstructed the circuit in multisim and the voltage divider with load resistance circuit is displayed. Next slide, please. For the next figure, we connected two multimeters to the circuit to measure the input and output voltages. We placed the multimeter near the function generator for the input voltage, then placed the second multimeter near the load resistor to measure the output voltage. The value for the input is 707.119 millivolts, and the value for the output voltage is 4.428 volts, where both of these values will be important to determine our cutoff frequencies. So next slide, please. Bearing in mind, I would also like to add a bit of context. Looking at the waveform for the output voltage, there is a little bit of clipping being involved, which can be from several causes like high input voltage signal. So maybe lowering it will show a sinusoidal wave instead of a clipped wave here in this figure. So moving on, next slide, please. For the computation part, we use both of our input and output voltages to compute for the mid-band voltage gain and the mid-band voltage gain cutoff, and as well as our target output voltage. So using equations 3.1 and 3.2 and 3.3, we get the values. So next slide, please. So for our mid-band voltage gain, we get 6.262. For our mid-band voltage gain cutoff, we get 4.4279. And for our target output voltage, we get 3.13 volts, where this target output voltage will be useful to find our cutoff frequency. So next slide, please. So here we change the frequencies so that the output voltage reaches that target output voltage 3.13 volts. And as you can see, at 153 hertz, we can find that the output voltage is approximately at 3.13 volts, making it our low critical value. Next slide, please. Then for the out, then for the high cutoff frequency, uh, changing the frequency to 35 megahertz also nets the target also reaches the target output voltage of 3.13 volts. And then next slide, please. With both cutoff frequencies here, we can now solve for our bandwidth, where the formula for the bandwidth is just subtracting those two values. Then after the computation, we get 35.998 megahertz, meaning that that the high cutoff frequency mostly dominates the low frequency in these figures. So next slide, please. So for figures 1.5 to 1 to 15, we will see here the where we change different values for the frequencies and then check their output voltages. So next slide. So here we don't need to focus too much, since the only thing you need to look at is the output voltages, where there's that you can see where it increases. Next slide. Slowly increases. For example, we have 4.09, then turning into 4.65. Then next slide, please. Then reaching 4.71 to 5.53 volts upon reaching megahertz. The values computed will be further discussed in the next slide by Kit Sally. And next slide again.
All right. So as we see earlier, figures 1 to 15, here on table 1.1, it summarized those computations. So this shows that the voltage gain of the transistor amplifier increases as the input frequency rises. So at a very low frequency, it shows that the gain is extremely small, indicating poor amplification. So as the frequency increases, such as from 100 hertz to 10 kilohertz, so the gain rises significantly, which shows an improvement in amplification performance. While from 30 kilohertz to 5 megahertz, the gain remains relatively high and stable. So it indicates a consistent amplification in the range. So next slide, please. All right, as we can see, this is the continuation of our table. So next slide, please. All right, moving on the bold plot. So this figure 1.5.16 shows the bold plot magnitude. So with respect with the bandpass characteristic, where the gain is very low at low frequencies, so it increases to a flat region, then decreases at the high frequency. So basically, it indicates that the system effectively passes the range of the frequency while attenuating the signals outside the range. So next slide, please. So for the conclusion of our experiment 3, the experiment really shows that the voltage gain of the transistor amplifiers depends on the input frequency. So the gain is very small at a low frequency, increases in the mid-range, and the remaining high at higher frequency, which confirms that our frequency are very dependent as a dependent response. So at a low and high cutoff frequency were identified basically earlier, result to a wide banded. So this also highlights that the importance of proper biasing in our measurements, while observing those clipping demonstrate that the limit of linear operation. So overall, the experiment is very successful frequency response behavior to the transistor amplifier. Yeah.
And that concludes the laboratory report of Group 1 from CPE 201. Thank you for listening.